Okay, this is where we ended last time. So let's look at how we measure pressure gradient force on a weather map. On a weather map, you'll see all of these lines that are called isobars. And isobars are lines that connect points of equal pressure. ISO means equal, bar, of course, for barometric pressure. If those isobars are spaced closely together, then that indicates areas of low pressure on a weather map. If they're widely spaced, that indicates high pressure. And the greater the difference between areas of high and low pressure, the higher the wind speed is going to be. So let's look at what a weather map might look like. Here you have areas of high pressure, and this is a typical weather map. Oops, let's go back. Typical weather map. High pressure here. You see that the isobars are widely spaced, and then air is moving from high to low, just not straight line because Coriolis, which we'll talk about next, high to low. So it's moving clockwise out of a high, counterclockwise into a low. We'll talk about why that happens in a second. But what you're paying attention to right now is just the spacing of the isobars. Where they're wide, that indicates higher pressure, that indicates low wind speed. Where they're close together, the pressure is going to be lower, steeper. We call that a steep pressure gradient. So you have no problem understanding that when you have a steep road, think about riding a bicycle down a steep road, you're going to go faster, or where a river is flowing in a steeper part of the river, the water is going to go faster. So the same thing happens here. Where we have these closely spaced isobars, the wind is going to be moving faster. And we'll talk more about this later, but over to the side here, you see these symbols. That's one way on a weather map that we can indicate wind speed. And you see that you have these different little tick marks. Every time we get more tick marks, the wind speed goes up until we get to flags and the wind speed gets higher. So one flag on the stick indicates 55 to 60, and then we can go up higher and higher and higher. So you see that the wind speed is much higher in the area where the low pressure is than it is over here where the higher pressure is. So isobars. We'll figure out why that we have this circular motion in a minute. Then this shows again just strong winds in here. Look how closely spaced the isobars are. Let me grab the little pen here just in case I need it. Let's use purple. So you see the close spacing. What happened to my pen? One of these days I will get used to this, maybe not. Right through there, strong winds through there. And again, here we have high pressure over here, light winds, strong winds over here where the isobars are closer together. So then we have the Coriolis effect. Coriolis effect, again, is the second force that acts on the motion of wind. And Coriolis is an effect that is produced because the Earth rotates. So anything that is flying or flowing in water or through the air is going to be deflected by the fact that the Earth is rotating underneath it. A good example would be an airplane. If we have an airplane and we're flying from the North Pole on a non-rotating Earth, you see what happens here. We're flying from the North Pole down to the southern hemisphere, and I can't make this do what I want it to do, so forget it. Flying from the North Pole, we were looking at the diagram to the right. On a non-rotating Earth, if we flew from the North Pole down south, it would just be a straight line motion. So our path wouldn't have any deviation at all. That's a non-rotating Earth. But think about a plane flying and the Earth rotating underneath that plane. If the pilot doesn't take into account that the Earth is rotating underneath the plane, then he ends up in a totally different location than his target area. So in the northern hemisphere, the Coriolis deflection is to the right of the original direction. If we're in the southern hemisphere, it's to the left of the original direction. And that's just because of our difference in perspective. At the equator, there's no deflection at the equator. And in the polar regions, that's where we have maximum deflection. And also the deflection will increase as wind speed increases. So we get this curvature that's taking place now. The wind isn't moving in a straight line motion. It's slightly curved as a result of the Earth rotating underneath it. And it not only happens if something is moving from north to south or south to north, it will happen if something is moving from west to east or east to west. So when PGF and Coriolis are in balance with each other, as they are higher up in the atmosphere, there is something called a geostrophic wind that's produced. What you're looking at, this flat kind of blue plane that you're looking at here, if you look to the side, you see 912 millibars over here, 908 millibars, 904 millibars. That means that the pressure is decreasing, and we know that happens as we get higher into the atmosphere. So the pressure is decreasing as we go upward. Well, at some point, Coriolis and pressure gradient force are going to be in balance with each other. And the wind then will be moving parallel to the isobars. So we call that wind, we call that a geostrophic wind. You probably know that better as the jet stream. The jet stream, sometimes they're described as these rivers of air. Jet streams steer storms, and jet streams never stay in the same place. They never stay at the same speed. If you have flown from California to the East Coast, you know that your flight is an hour shorter than if you're flying back. That's because flying from west to east, the pilots will get into the jet stream. They have a tailwind. So it helps save on fuel. It helps save on time. Coming back, they don't want to be in the jet stream because that's a headwind. So the trip back is about an hour longer than the trip out to the east. So the jet stream flows, it changes from about 12,000 to 80,000 feet high. Again, it blows from west to east, and it also changes speed. And pilots will talk to each other about where the jet stream is. Is it feasible to get into it? Is it going to be saving on fuel and time to get into it, or should we avoid it? So there are two jet streams in the northern hemisphere. We have the polar jet stream, and this is the one that we usually hear about. If you hear the meteorologists giving a weather report, they'll be talking about storms being steered by the jet stream. The jet stream has dropped down to the south, so that allows colder air from the north to get to us, or the jet stream has a kink to the north in it, so that allows warmer air from the south to go into more northerly regions. And again, it's changeable. It changes from day to day, maybe sometimes from hour to hour. So that is the more powerful one. Then there's a subtropical jet stream. This one affects us a lot of times, especially during El Nino years when we hear about these pineapple expresses that are bringing a lot of moisture to us. They're called pineapple expresses because the rivers of moisture seem to be coming from Hawaii, and they're steered by that subtropical jet stream. And this just happens to be an image showing that. Here's Hawaii. Let me see if I can pick this pen up again. I don't know why I'm not able to, and I know you all are tired of hearing me whine about it, but what am I going to do? I have to whine to somebody. That's okay. Maybe this will do. I don't know. Anyway, that's not right. There's the atmospheric river, and it's headed right to California. The bluer the color, the more water vapor that's in the system that's headed our way, so we can expect to get a lot of moisture dumped onto us. All right, let's clear that and go on to the next. And there's that pin showing up. And every time I do that, it doesn't want to move. Clear my drawings. Let's go to the mouse and there. Let's see if that works. No. Okay, hold on. All right, let's go. Let me pause this for a minute. Okay, so then that brings us to friction. So again, there's pressure gradient force, air moving from high to low. There's Coriolis, that air is going to be deflected to the right in the northern hemisphere, to the left in the southern hemisphere. Then there's friction. Friction comes into play closer to the surface, where we have mountains, where we have forests, where we have buildings, and friction acts to slow air down. So if air is slightly deflected and it slows down, it's going to be more curved. Now remember, up there where the jet stream is, there's no friction. So the air just moves. It's not being impacted by friction at all. So those three forces together, PGF, Coriolis, and friction, allow us to come up with a general model of atmospheric motion, or the general model of the wind systems. So this is how it looks at the surface. Air that was deflected is going to be more circular. There's going to be more of a circular circulation, if you will. Gives air this curved movement. So if we look at the high pressure system over here, we see that air is moving out of the high into a low. So we say that air is diverging out of that area of higher pressure. Remember, air always moves from a high to a low, which is not doing it in a straight line motion now. It's doing it in a more curved motion. So air moves out of the high in a clockwise manner in the northern hemisphere, counterclockwise into an area of lower pressure. So air is subsiding in a high pressure system, and remember, sinking air is stable air, and it's converging into the low pressure system. That's one of the ways that we have air becoming unstable. When it converges, the only place it has to go is up. So convergence gives us convection, rising air, and you see the arrows. I would try to grab a pen here, but I always screw it up when I do. Let's see if I can do it. Okay, so we see the air converging out of the high into the low, and air rising in the low. Rising air is associated with instability. That's why low pressure systems are associated with instability. When we have a high pressure system, there's not much of anything happening. Sky is usually pretty blue. Low pressure system, we don't actually have to have a storm when in a low pressure system. It might be that we just have clouds that are showing up. We don't have to have a thunderstorm. We don't have to have a hurricane for it to be a low pressure system. Rising air will give us clouds too. So in the northern hemisphere, that low pressure system gives us what we call cyclonic flow. That's why low pressure systems are sometimes referred to as cyclones. The high pressure system gives us anticyclonic flow. The circulation is all reversed in the southern hemisphere because Coriolis is a different direction. So a high pressure system, air will be moving counterclockwise out of a high, clockwise into a low. Still, a high and a low are associated with the same type of weather conditions. It's just that in the southern hemisphere, the circulation is going to be a different direction because Coriolis is a different direction. So this is Hurricane Floyd. Hurricane Floyd was a hurricane that wreaked havoc in North Carolina and South Carolina. I think it was in 1999, but never mind that. What you're looking at here is this counterclockwise motion into the center of lowest pressure here. Hurricanes are distinguished by this eye that they have, which is an area of clear from the top of the storm to the bottom of the ocean, no clouds. We'll figure out why when we get into the next chapter. Then this is another type of weather map that we can look at. This is just showing the isotachs, which are the wind, showing the wind streams, how the air is circulating, and you can see that it's circulating counterclockwise into that center of lowest pressure here. And then in the southern hemisphere, it'd be totally different. Here's a cyclone, and notice that it has that counterclockwise, though you're not going to be able to see that pin because it's the same color as the globe. That's clockwise into the center of lowest pressure. Here's another view. Ooh, why did that do that? I hope you are used to me flubbing up on this many times. So that is a hurricane in the South Atlantic, one of the first ones ever recorded in the South Atlantic, because usually the water is too cold, global warming again, and you see the clockwise motion. Should I try this? Clockwise, like the hands move on a clock, clockwise. Here are the rain bands moving clockwise into the center of lowest pressure. All right, so this is airflow on a uniform Earth without Coriolis. Air would move from high to low. Cold air in the polar regions, so cold air is heavy and dense, so air would be sinking. In the tropics, the air is warm, so warm air rises, so we'd have air rising in the tropics, sinking in the poles, and we have this simple, this is really called a convection cell right here, just a simple convection cell where we have warm air, let me get this up here, warm air rising here, sinking here, and that single cell, very simple, single cell is called a Hadley cell. It's named after the British scientists that first described that type of motion. Just a simple convection cell. Warm air rises, cools off, cold air sinks. So that's how it would be if only pressure gradient force was at work on air movement on the globe. But it's not the only force at work. Earth rotates. There's no getting around that. So that throws Coriolis into the equation, and Coriolis is going to give us this deflection, and then with friction in there, that gives us more of that circular motion that we are familiar with from looking at weather maps in a high pressure system and a low pressure system. So these are the global wind systems that are produced by those three forces. In the northern hemisphere, we have what are called the polar easterlies, the westerlies, and the northeast trade winds. We live in mid-latitude areas. Most of North America is in the belt of westerlies. That's what in California, it's the westerlies that steer our wind systems, air moving from west to east. Then in the southern hemisphere, we have the southeast trade winds, the westerlies, and the polar easterlies. So sort of this mirror image of everything in the southern hemisphere. So if we look at these wind belts on a map, this is what we get. Up here in the northern hemisphere, in the north, we have the polar easterlies. So that air started moving south, but Coriolis caused it to be deflected to the right. And if you're standing up here at the North Pole looking at that wind, then you see that it's deflected to your right. So winds are named for the direction that they come from. So the polar easterlies are coming from an easterly direction. East is over here. West is over here. So the winds are moving from the east. So that wind belt is called the polar easterlies. Now let's look down here around the equator. We have air that begins to rise, warm air rising here, and it begins to make its journey up to the polar regions. Remember, Mother Nature trying to balance out things. But some of that wind cools off. And when it cools off, it begins to move back to these warmer areas, high to low. And when it does, at the surface, the winds are going to look like this. Again, if you're standing up here, I'm going to really mess this up. This is my stick man, sort of. And if stick man is standing up here looking at the air moving, it's going to be deflected to the right. So that belt of winds is known as the northeast trade winds. Okay, so that gives us our polar easterlies and our northeast trade winds. Well, a portion of that wind, that air, I should say, that started making its way to the polar regions, a portion of it keeps on going. And Coriolis will now deflect those winds. Let me get my thing here. Will now deflect those winds to the right, because now we're standing, oh, Lordy, I need something more than this that I can draw with. So now we're standing here, watching the air move, and it moves to our right. So now those winds are deflected from west to east. So they're blowing from west to east, and they're called the westerlies. Okay, so the polar easterlies, let me get rid of you, the polar easterlies, the westerlies, and the northeast trades. And we have mirror image in the southern hemisphere where we have the southeast trades, the westerlies, and the polar easterlies. Okay, so the trade winds, if you've had a history class, you know that the trade winds, that's how people from Europe ended up getting to the New World. They would get in that belt of northeast trades. Remember, there was no diesel, there was no gasoline, all they had was wind. There was no nuclear power, all they had was wind. So the wind would blow them over to North America. Then when they wanted to go home, they would get into this belt of westerlies here, and that would take them home. They might have a delay when they got caught in the doldrums, but we'll talk about that in a minute. So that's circulation on a rotating Earth. And we see how, remember, there are two types of pressure systems. There are thermal highs and lows. That's what starts it all. But then we have these dynamic highs and lows. So if we look at our global wind belts, and then we see how that dynamic motion in the global wind belts over here on the left here are going to give us our pressure systems on the right. How does that happen? Remember, in a high pressure system, we have air that diverges out of a high pressure system in a clockwise motion. In a low pressure system, air is moving counterclockwise into an area of low pressure. So let's just concentrate on the westerlies over here and the trade winds, the northeast trade winds. If you look at the circulation here, let me get this pen. So the circulation here, this is so messed up. You all aren't going to understand that, but this is clockwise. That's clockwise. So the air is moving out of a high pressure system into a low. And here we have if you look at the polar easterlies and the westerlies, we have counterclockwise motion. So there are subpolar lows. Now, if we didn't have these big land masses, we would have a zone of low pressure, we would have a zone of high pressure. But the land masses break these up into these semi-permanent high and low pressure systems. And in the northern hemisphere, we have names for them. There are also names for them in the southern hemisphere, but since we don't live in the southern hemisphere, we're not going to worry about that. We want to know the names of the two low pressure systems, one on the eastern side of North America and one on the western side of North America, and the two high pressure systems, one on the east side and one on the west side. These are responsible for the climate. If you want to, we have traveling highs and lows, and those are more responsible for the weather, and we're going to talk about those in the next chapter. But these are more responsible for the climate that an area has. So I'm going to move away from there and go here, and then we'll go back to those and we'll look a little bit more closely at what happens. So the low pressure systems that are formed from the counterclockwise motion of the easterlies and the westerlies are the Aleutian Low on the western side of North America. That's where these systems break out of in the wintertime that bring us our unstable weather in California. Then on the other side, in the eastern side, we have, I hope you all can see that, we have the Icelandic low. Then here in the Pacific, we have the Pacific high, and over on the eastern side of North America, in the January map, it's the Azores high. So I'm going to flip between January and July pressure map, and I want you to see how the pressure changes. See that? That purple line represents what's called the intertropical convergence zone. That's where there are thunderstorms all the time. Basically every afternoon they've got some kind of weather, some kind of rain coming out of those clouds. I'll go back to January. See that? The Pacific high moves to the north in the summertime. Go back to January. It shrinks to the south in January. Oops. So there it is. That dominates, that high pressure system dominates our weather in the summertime. We have hot, dry weather, hot, dry weather. All of our rain comes when that Pacific high shrinks, I keep doing that, shrinks back to the south, allowing that Aleutian low to grow. So these unstable weather systems break out of that Aleutian low and give us our unstable weather here in the wintertime. July, January. Now the other thing that sometimes people have questions about is, okay, if we have the western part of North America dominated by a high pressure system and the eastern part of North America dominated by a high pressure system called the Bermuda High, how come the climate is so different? Well, you have to look at the circulation. We are on the sinking side of that high pressure system. Air is descending and sinking air is stable air. Look at people in Florida, Georgia, North Carolina, South Carolina. They are on the rising side of the Bermuda High. And rising air is unstable air. Think about your recipe for a cloud. Water vapor, is there going to be water vapor available here? Cooling temperatures available? Yeah, because the air is rising. And of course, they're going to be condensation nuclei. So we have water vapor, we have adiabatic cooling, so we have plenty of rain. The climate system in that part, in that neck of the woods is, you know, subtropical kind of moisture basically all year long. Not for us over here though, because we're on the descending side of that Pacific high. The ITCZ, look how it moved in July. It moves with the high sun. Remember where the sun is overhead in July. It's overhead at the Tropic of Cancer. So these pressure systems move with the high sun. There it goes, shrinks back. Now, even though the ITCZ moves, the Intertropical Convergence Zone moves, there are certain areas where it always influences these places. And that's where we have tropical rainforests, like in the Amazon basin, the Congo, places in Indonesia. They are under the influence of that ITCZ all year long. So the subpolar lows formed by the convergence of polar easterly winds and the westerly winds dominate weather in winter when subtropical highs move south with the high sun, characterized by cool, moist air. Western North America dominated by the Aleutian low, Eastern North America dominated by the Icelandic low in winter. Polar highs formed because of the heavy cold air in polar regions. Antarctic high, stronger, more persistent than the Arctic high. Then the intertropical convergence zone formed by the convergence. Remember what happens when air converges. The only place it has to go is up, and rising air is unstable air. And we got plenty of moisture availability because most of this is happening over the oceans. Formed by the convergence of the northeast trade winds and the southeast trade winds. Plenty of available moisture allow clouds to build up, characterized by clouds and rain. The sailors back in the day called these areas the doldrums because it was the same weather day after day. Hot, muggy, cloud buildup, rain. Start all over the next day. Hot, muggy, cloud buildup, rain, thunderstorms. Subtropical highs form between 20 and 35 degrees latitude in both hemispheres. Sinking, stable air. Sinking air is stable air, so clear and cloudless skies. Sailors called these areas the horse latitudes. Sometimes they would get stuck because the wind would die down. Sometimes they would get stuck for weeks at a time in the horse latitudes. And legend has it that it's called the horse latitudes because they would throw horses overboard because they were competition for food and water. That makes no sense to me. It's never made any sense to me because if you're desperate for food, it seems like you might have killed a horse. I wouldn't want to eat one, but you know, if you're starving, who knows what you would do. So formed by the circulation of the westerly winds and the northeast trades. The Bermuda High affects southeastern U.S. in the summer, the Azores High in winter, and the Pacific High dominates the western U.S. in the summer, sinking on the descending side of that high pressure system. So the stable side of the high pressure system. And we'll stop with that. We go back here so that you can get another look at these. That's where we'll stop for the day. So see you next time.